All right, so let me kind of summarize what we have done so far. Um, so recall that given the random variable x, the moment generating function is either tx, and the cumulant generating function is log of e. Now remember that this begins by, it's the basic k going from 0 to infinity, m sub k, t to the k, over k factorial, where k is the k factorial. K is the kth moment, k is the, m sub k is the kth moment of the thing. And suppose we have, well, the point is, oops, this is not the right side. The, somebody crying?
No, this is
This is the Jacobs.
Oh, the jackals.
Group of jackals.
I see. Ooh. Yeah. The zeroth moment of the thing is, you know, the expectation of the x to the power 0 was the density function. But that's 1. X to the, right? So m0 is 1. So this can be written as, let's say, s1 plus s of t, higher powers. So this is equal to m sub 1 t, m sub 2 t squared over 2 factorial, dot, dot, dot. Therefore, the log of this thing is log of 1 plus s of t. And so this proceeding formally is the log of 1 plus m1 t plus m2 t squared over 2 factorial dot, dot, dot. Keeping in mind that this is my s of t. So what do we have? We have, remember, recall, minus log 1 minus x is summation x to the n over n, which will be used repeatedly in this thing. So this would be that, and then log of 1 plus x, therefore equals, I just put minus x there, so it would be x minus x squared. It's an alternating series. It's an alternating series. So log of 1 plus s of t then therefore will be the alternating series s of t, s of t squared over 2 dot, dot, dot. So when I write down this thing, it will be m1t plus m2t squared over 2 factorial dot, dot, dot minus m1t plus m2t squared cumulant generating function was defined, and so we defined log of e to the t x summation, I think I used like kappa, k, or whatever I used, case of n, t to the n over n factorial. And as you can see, it starts at n equals 1 to infinity. That's the general way this whole thing proceeds. So in particular, k1, which is the first cumulant, is the coefficient of t, and there's m1 there. These are going to be higher powers of t. So k1 is m1. What's the second cumulant? Well, it's going to be coming from, we check here, it's m2, and, well, there's a half here somewhere, I forgot it.
Yeah.
There's a half here, sorry. There's a half here, okay, good. So, you can see that, K2 is going to be M2 minus M1 squared. Good, the twos keeps track, right? And as you can see from here, it's combinatorially messy, but it's clear that the higher cumulants can be given in terms of the moments. So there's a
2 minus m1 square by 2.
Pardon me?
m1 square by 2.
There's a 2 here, M2.
Oh, I see.
That is coming from ST.
Yeah.
Factorial.
If you're right, the Riemann hypothesis is false. Okay, all right. So this is what we have, and you can see now that these higher cumulants are all can be expressed in terms of the moments. So there's general formula, and I'm not going to discuss this combinatorics. It's a beautiful chapter in combinatorics, Bell numbers, blah blah blah, and all the stuff that comes in. Beautiful formulas are there. So in general, case of n can be expressed as a polynomial in the m sub k's. Okay, so this is what we have. Notice that this is the second moment of the, this is nothing but e of x minus mu, the variance. Remember, the variance of a random variable is the expectation of x minus mu squared, and it turns out to be expectation of x minus mu squared. So K2 is a variance, and therefore K2 is always non-negative. In particular, I don't want to put a factorial there because that'll be K2 is bigger than equal to 1. Okay, anyway, now we just keep that in mind as we proceed. So yesterday we showed that h of y exists, which is always non-negative, and is a probability density, and h of y over y are both probability density functions. Such that two times c of s is the integral 0 to infinity h of y over y 2, 1/2, S minus 1, gamma S over 2, zeta S. So this was the formula we had. We proved the existence of this probability density function, thus giving a probabilistic interpretation of C of S. Thus giving a probabilistic interpretation of C of S as the expectation of y to the S with respect to this density function. Of course, S is a now complex variable. There's nothing stopping you from doing that. So, get that. Now, so K2 is always positive, so keep that in your head. We use the theory of Hadamard products to study C of S by Hadamard factorization. We showed that 2 times C of S is the product 1 minus S over rho. Right? And keeping in mind issues of convergence, we just pair things up and don't really bother things about it. You can pair rho and rho bar, but it's more elegant to write it this way. More elegant and more suggestive. Now we have the functional equation C of S is equal to C of 1 minus S. By the way, C of S is an entire function, keep also that in mind. C of S is equal to C of 1 minus S. That implies that 2 C of S is equal to product rho 1 minus S over rho. And therefore, if I were to take logs of both sides, we would end up getting that. And then use the log expansion to get a Laurent expansion of C of S around S equals 1. So we get a Laurent expansion at S equals 1. Big K minus 1. 1 over rho of K. Right, let me just expand. Pardon me?
All term will be negative.
Because 1 minus x,
1 minus x.
log of 1 minus
One.
x,
Yeah.
that is minus of all negative.
Oh, sorry, log of 1 minus x. What you're saying, there should be no sign at all.
Yeah.
You're right, absolutely right. But I want a Laurent expansion at S equals 1, so usually Laurent expansions go this way, don't they? Yeah, that's why I was fixated on the sign. Yeah, you're absolutely right, there's a minus sign there, and then the Laurent expansion goes like this, not 1 minus S. That's where I'm trying to figure out what the expansion is around S equals 1.
one whole power k should not be this.
Why not?
Acha, acha,
Because I've got a 1 minus s, you see here, and I want the expansion around s equals 1. That's all. That's where I was putting my,
Twisting it.
I had it in my head that was a 1, but you're right, that's the minus sign. Okay. So we can interchange the summation log 2 CS then equals minus summation k goes from 1 to infinity of summation row 1 over row to k times minus 1 to the k over k s minus 1 to the k. This is the Laurent expansion, and these are the numbers. These all of row to k's. So we have this. Now I want to keep this in the back of the mind and mention that what is Lee's criterion? What is well, Lee's criterion defines these numbers this is the definition. By the way, all these summations over rows are always over non-trivial zeros. We don't worry about trivial zeros at all anymore. So you have this over non-trivial zeros. And Lee's criterion is that lambda n are non-negative if and only if the Riemann hypothesis. Okay. And what I would like to say is that somehow or other this object is connected with the lambda n's. And the theorem I want to prove, I can get my hands on lambda n. Is 1 over n minus 1 factorial, I believe. dsn of s to the n minus 1 log 2 c s. So I take the nth derivative of this mess and evaluate it at s equals 1, and out will pop lambda n. Okay, so let's see how that works. That's one way of, so we're going to try and see what these lambda n's are, first from the context of C of S, and second from the context of this probabilistic interpretation. See what they mean. Okay. So I got this here, so I can drop this on. So you all know Leibniz's rule for differentiation, right? Good. So let's look at, consider, so by Leibniz, we have d to the n dsn of this stuff. its rule, right? And choose K. It's actually the product rule generalized, okay? How do you differentiate a product of two things? Generalize it, okay? It's that. Notice that I have a polynomial in n of degree n minus 1. If I differentiate it n times, I get 0. Therefore, the sum is not really going up to n when it's actually going up to n minus 1. Because it's 0. Now, and these are pretty simple things to differentiate. As you can see, if I differentiate s to the n minus 1, I get n minus 1 s to the n minus 2. And I have to evaluate this silly thing at s equals 1. So if I'm putting this s equals 1, let me just do it this way. So therefore, this guy evaluated at s equals 1, evaluated at s equals 1 equals summation k going from 0 to n minus 1, and choose k, and every time you so it's differentiated once, you get n minus 1, differentiated k times, you get n minus k, and then here I have to look at this expansion. This coefficient is the derivative at 1, kth derivative at 1 divided by k factorial. So I need the n minus 1, kth one, so therefore I need the n minus k. So there's no that expression over there. Summation rho 1 over rho to the n minus k minus 1 to the n minus k over n minus k. That's what that is. If I evaluate this thing at s equals 1, that's what I get. Everybody with me? A lot of this simplifies. So what do we get? We get here the n minus k and the n minus k here cancel, so I get n minus k minus 1 factorial. Combined with this, I get an n minus 1 factorial. Summation rho 1 over rho the n minus k, and there's a minus 1 the n minus k. Coming out to be neat. The n minus k here cancel this first n minus k. I got n minus k minus 1 factorial. Combining that with n minus 1, I pull the n minus 1 factorial out. All that mess is gone. Then I have n choose k and the summation over rho of this. Am I missing something? You have the look of that I missed something. So this looks like a binomial expansion once I interchange. I interchange it. So n minus 1 factorial, summation over rho. Oh, I know. You're thinking I forgot a sign. The minus sign. You're right. So where was that sign? It was so up to here, and at this point I should put a minus sign. Thank you. Indian students are usually polite. They don't tell you I forgot something. Okay, so this is, you're absolutely right, there's a minus sign. And now, what do I have? I have so rho times summation k going from 0 to n minus 1, n choose k, minus 1 to the n minus k, over rho to the n minus k. And this looks like some sort of binomial thing, but there's a term missing. The k equals n term is missing. But the k equals n term corresponds to 1. So therefore, this is nothing but 1 minus 1 over rho to the power n minus 1. Therefore, this is nothing but n minus 1 factorial So you have this nice formula for lambda n in terms of this. Why is this important? Because this gives a probabilistic interpretation of the lambda n's. Because log of 2 xc of s is already the expectation of y ts, and log of that is the characteristic function of the generating function for the cumulants. So the cumulants of this distribution are stuck in here, and therefore we have a probabilistic interpretation of the lambda n's. That's what we have. So this is one point. Is it okay to rub this up? Sometimes it's not a good idea when people are still copying things down. I'll rub off the top part. Okay. So this is one interpretation of the lambda n's. I want to get another interpretation of the lambda n's using another function, which is essentially c, but put 5s to be c of 1 over 1. Okay. And by the functional equation, this is equal to c of 1 minus 1 over 1 minus s, which is equal to c of, well, 1 minus s, 1 minus s minus 1, which is minus s. Therefore, phi of s is also equal to c of s over s minus 1. Now, we had the Hadamard factorization. I think, can I rub this bottom part off? Okay. For those people who are copying, okay. Now, by the Hadamard factorization implies that c, phi of s is equal to product over rho 1 minus s rho over s minus 1, right? Sorry, s over s minus 1 rho. The rho is on the bottom. Remember, it's 1 minus s over rho, but I put this argument s over s minus 1. I kind of did this yesterday. I'll do it again. So you have s minus 1 rho. Don't worry about conversions. As I told you, it can always be justified by pairing rho and rho bars all the time. So don't worry about that. So you have s rho minus rho minus s. And we decided that we divide top and bottom by rho, and we get s minus 1 on the denominator, and we get s minus 1 minus s over rho, and changing the signs, top and bottom, we get 1 minus s, 1 plus s over rho, minus s, which gives me product rho, 1 minus s, 1 minus s, 1 minus 1 over rho. I will talk about the meaning of S over S minus one and one over S minus one. These are conformal maps, you know, and why do they work, we'll see. So you get something like this, so that now log phi s is equal to summation rho log of 1 minus 1 over rho s minus log 1 minus s. Now keep in mind you can't go around separating these things, you have to keep them together. Otherwise you get a divergent series. And now we have expansions for log of 1 minus x, so we just use that. So it's a, what did we decide? It's a minus sign, I keep forgetting the minus sign, rho, and here we have summation k going from 1 to infinity, 1 minus 1 over rho, let me put n equals 1 to infinity, 1 minus 1 over rho to the power n, and then here, so, yes, is it a plus or a minus?
Yes, yes.
What did you say?
Yes, you are taking it out.
Well, I'm going to take it out, yeah. I'm going to put it in here. Looking at the expansion of logarithm, which is 1 minus 1 over rho to the power n. That's got a minus sign, but this has got a plus sign, so I compensate. So this is exactly, so if I interchange summation, n going from 1 to infinity, I have precisely, oops, there's one problem. I forgot something. Yeah, it's correct. This I'm off by one factor. Okay, let's just go on. This is looking like, I mean, it's not going to be terribly important, but anyway, it's looking like it's lambda to the n, lambda sub n, s to the n over n. That's what it's looking like. The power series expansion.
You have minus 1 there, but lambda is sort of different the other way.
Pardon me?
There's minus sign outside.
No, there's a minus sign outside.
Ah, okay.
Yeah. So but anyway, it doesn't matter for the discussion, but that's what you were getting. It could be there might be a switch later, but that's going to be irrelevant. What I need is that the lambda n's are appearing here, whether it's lambda n plus 1 or lambda n. I when I was doing it this morning, I got lambda n plus 1. Maybe I made a mistake. Okay, which is possible. Yeah, actually, this is fine. This is fine. Yeah, this leave it. Oh, I know what I was doing. Yeah, so what I was going to do is I'm going to take the logarithmic derivative. And then, of course, I'm right, yeah. It compensates, because the n cancels and I get an n minus 1. That's okay. So that's okay. Now, do I need this? I don't need this anymore. so therefore, plus keeping in mind that 5s is C of S over S minus 1 is equal to, if 5s is this, then log 5s is equal to summation n infinity lambda n s to the n over n. Now, for those of you who know some algebraic geometry, will know that the zeta functions of curves and varieties have some sort of expansion where usually this is the number of points on the curve or something over the finite field of QDN elements. This is really the motivation for Lee to be looking at these things in this way. He was trying to push the classical Riemann zeta function into a shape which resembles the zeta functions of varieties, so that maybe some of the methods that were used there can be used here. And in that process, he came up with this positivity criterion, which is another very important positivity criterion in algebraic geometry. It's called the positivity of the Rosati involution, working on a certain algebra. And because it's positive, the Riemann hypothesis pops up in the case of algebraic geometry. That's how it's proved. So if you can somehow interpret, first get a positivity criterion, and then interpret this. Here we don't have points on curves. We don't have a curve. So probability is somehow one of the main perhaps motivations for trying to bring some meaning into these expressions. Okay. Now, now that I have, I think, more or less many of the things that I need, this formula will be useful, so I want to copy it somewhere. Need this formula later on. Keep it there. Okay, we need this as well, so we'll keep this here. Then I can rub off everything else. Now I can prove Lee's criterion in a very simple way. I don't think this is in the books. Lee's proof is not easy. Bombiri and Ligarius give a more generalization of it, but in the process complicate matters. So this proof is,
Landau's theorem, right? That's one.
well, we're going to use Landau's theorem, but he doesn't use it.
Oh,
He doesn't use it, yeah. You have to, if you use Landau's theorem, it becomes simpler. So let me prove Lee's criterion then, using, as Professor Prakash has said, Landau's theorem. Let me review Landau's theorem or whatever. So recall, if you have a power series with real coefficients, non-negative, has a finite radius convergence, R, say, then So that if you haven't seen it, I'll give you the one-line proof of this fact. Without loss of generality, we can assume R is 1, because if you just take x over R as the argument, I can just replace x by x over R, and the radius of convergence would be 1. So without loss of generality, assume R equals 1. And so it's analytic, we have inside R equals 1. And so suppose we look at the expansion, look at the Taylor expansion about x equals a half. So f of x is equal to summation a sub n x minus a half plus a half power n summation and choose k 1 half to k x minus a half to n minus k take on from 0 to n. So I'm just taking the expansion. So this way I get my expansion around x equal to half, and I would naturally interchange summation. Oh, maybe it's not a good idea to do it that way. Do just 1 over 2 the n minus k here, because I want to get the expansion about k. Put the k there. Okay. Then we have k equals 0 to infinity. Here, k is less than or equal to n, so n has to be greater than or equal to k, right? Summation, n has to be greater than k, a sub n, and choose k, 1 over 2 to the n minus k, and all this gives me x minus a half to the k. This is the expansion, this is the power series expansion about x equals a half. Okay. Now, if there is no singularity at r equals 1, then that means there's a small neighborhood. I can put x equal to 1 plus epsilon. There's a small neighborhood in which the function is analytic. We put that in, so when I do that, I get f of x. By the way, I can interchange this thing because of the non-negativity of everything. Remember, when I recalled Fubini's theorem, either non-negative or the whole thing is absolutely convergent. Well, everything is non-negative here, so it's fine. So f of x equals a going from 0 to n, 0 to infinity, and summation n together with k, a sub n, and choose k, 1 over 2 to the n minus k, times x, I'm putting x equal to 1 plus epsilon, so that would be 1 half plus epsilon to the power k. And now interchange some things again, okay? And then you find summation n going from 0 to infinity, summation k going from 0 to n, an's on all side, and choose k. This is now 1 over to the n minus k, 1 half plus epsilon to the k. So this is nothing but 1 plus epsilon to the power n, and therefore an 1 plus epsilon to the power n converges. Therefore the radius of convergence is not 1, it's bigger. That's it, that's the proof. And it's the same proof in Landau, classical Landau for Dirichlet series that many of you might be familiar with. Same proof. This is a power series version of the same thing. Okay? So that's good to know. And we're going to use that along with that elementary observation that I told you last time. Elementary observation. y squared is less than x squared plus y squared, if and only if minus 2x plus 1 is less than 0, if and only if x is bigger than a half. Okay, so that's the proof. And this means that if the inequality is reversed, if this is bigger, then the real row is less than a half. And if it's equal to a half. So corollary, real part of row equals a half if and only if the absolute value of row is equal to the absolute value of row minus 1. Okay, that's how there is to it.
You can think of this in terms of distances in the complex square.
You can, but for the time being, this is fine. And this elementary observation allows us to give a one-line proof of the easy direction of least criterion. Namely, if the Riemann hypothesis is true, all the lambda n's are positive. And why is that? Well, if the Riemann hypothesis is true, the real part of rho is a half. And therefore, what does this mean? It means that if I divide through by rho here in this equation, I would get 1 equals the absolute value of 1 minus 1 over rho. That means 1 minus 1 over rho is sitting on the unit circle. Okay? So if real part of rho is a half, if real part of rho is a half, then from here we see that 1 minus 1 over rho has absolute value 1. Therefore, we can write 1 minus 1 over rho as e to the I theta for some theta real. By the way, I should have pointed out at the very beginning that these lambda n's that we had, if there was any doubt, 1 minus 1 over rho, the n. If there was any doubt that these are real numbers, it's clear that they're real because if rho is there, rho bar is there too, as a 0. Okay, so these are real numbers, but now I've got this guy to be e to the I theta, so there will be one term here, 1 minus e to the I theta to the power n. But then there will be another one corresponding to the conjugate, which will be 1 minus e to the minus I n theta. Add them together, you get 2 minus 2 cosine n theta. Thus, each summand, the paired summands, let's say, thus pairing rho and rho bar gives a summand of the form 2 minus 2 cos theta, which is of course positive. So one way is easy, provided you made this observation. If you didn't make this observation, it's torture. And if you look at papers, they mess it up. Yeah. This is the key thing to get the trivial direction. The other direction is, of course, the Landau business. So this, if conversely, if lambda n's are non-negative, we consider the power series. Summation lambda n s to the n yes, so let me just put here, get some space. From here, logarithmic derivative So let's consider this power series. Whatever. All the coefficients are non-negative. And therefore,
Has to be n or has to be n minus one?
well, it doesn't really matter. It's not, if you like, I can do that. Yeah, so that it tallies with it, yeah. Okay, yeah, I think we'll keep it like this then. Then we have a power series with non-negative coefficients, and therefore, this has to have a singularity. Firstly, this being equal to phi prime of s over phi of s. And where did I put it here? Phi of s is xi of s. The xi function has zeros. Therefore, there are singularities. Therefore, this power series has a finite radius of convergence. So, okay, so it's a finite radius of convergence. And so the question is now, it has a singularity at its radius of convergence, which means that inside the circle of convergence, it's analytic. So this has a finite radius of convergence, R same, and for mod s less than R, this function phi prime of s over phi of s is analytic. Fair enough? It's analytic. Therefore, the radius of convergence, but by Landau, it has a singularity at s equals R. And where do those singularities come from? They come from the zeros of phi of s. Because remember, phi is an entire function, and it's an entire function. The only way this thing has singularities is that it's coming from the zeros in this guy. Okay. Now, the point is, the lambda n's are non-negative. I don't know if this is there. Of the two, I think one of them, yeah, this is the better one. So the point is that it's analytic inside, and hence log phi of s, which is equal to summation n going from 1 to infinity, lambda n s to the n over n, is analytic for mod s less than r. In particular, for 0 less than s less than r on the real line, we have log phi of s is bigger than or equal to 0. Because s is positive, the lambda n's are positive. Remember what I'm trying to show? Lambda n positive implies the Riemann hypothesis. I'm trying to show that, okay? So if they're all positive, log phi of s is non-negative. This is the classic, so in particular we certainly have log absolute value phi of s, actually. So this implies keep it like that. This implies that phi of s is bigger than or equal to 1. Now, as I approach R from the left, thus limit s approaches R from the left, phi of s is bigger than or equal to 1. So phi of R can't be 0. So if it has a singularity at s equals R, phi of R has to be 0. Which means phi has no singularity, has no 0 at s equals R. singularity at s equals r means phi of r is 0. Here I should have put phi of r equals 0. Comes from the singularities of phi prime over phi comes from the zeros of phi. So phi of r is 0 from this argument, but from this argument phi has no 0 at s equals r. Therefore, there is no what does this contradict?
Finite radius of convergence.
No, it contradicts the fact that
R is less than 1 by this.
r is less than r is less than 1. This implies, that's right, this implies that r equals actually 1. Which means that all the zeros of this function are on the unit circle. And we agreed that rho over rho minus 1 having absolute value 1 means real part of rho is a half. So these zeros. It has to be 1 because you see the radius of convergence has to be 1 simply because we know there are actually zeros on the thing. You know, on the half point. So we do know that 1 is the boundary because there are zeros on the zeta function on the critical line. Therefore, r has to be 1, and therefore this shows that r equals 1. Okay, so this implies that all the zeros rho of 5s have correspond have all the zeros rho of 5s satisfy that rho over rho minus 1 is 1, which implies that real part of rho is a half. So this is the other direction. So starting from non-negativity, you look at this power series, and you argue about the radius of convergence, and then you find that the radius of convergence has to be 1. The singularities, therefore, are sitting on the unit circle. If they're sitting on the unit circle, their real part is a half. Now, so the radius of convergence has to be 1. You can see now with this particular setup, you only have positivity.
Sir, if R is equal to 1, will that, can you say that log phi of s will go to infinity? Will go to minus infinity?
Well, for certain points at those zeros, yes, at those zeros. So to argue whatever the radius of convergence is, we know it's got to be less than 1, and it has to have a singularity at that by this at that point, yeah, at 1, but it doesn't.
Okay.
Yeah, but it doesn't. That's the argument. Okay, so now we've more or less finished setting up enough pieces of information to start to discuss the consequences of this. So, for example, from this formula here, we could use the Leibniz formula again. So, let's give name to the star. From star, lambda n is k, s to the other and its formula to separate these two pieces out, and we already found that this equals 1 over n minus 1 factorial. Summation k going from 0 to n, and choose k. And this is n minus k. So I'm going to, sorry, this has to be evaluated as equals 1. We evaluate this, sorry, this was s equals 1 evaluation with this formula. So we evaluate this at s equals 1, and you end up getting n minus k factorial here. And then these are, by the definition, the cumulants. I'm going to change notation because I've used k up here, okay? Kappa sub n minus k. According to the, let's see, I don't know how I defined it. I think there was a factorial floating around. Fair enough? So in other words, the n minus k factorial here cancels with this. The n factorial and n minus 1 factorial gives me an n. K goes from 0 to n. I think I took care of everything except factorial from the bottom here. N minus k factorial, kappa to the n minus k. In other words, the lambda n's can be written in this fashion. Now if we look at lambda 1 is just going to be n k 0 to 1. Did I have too many terms here? Let's see. Kappa sub 0 is always 1, I suppose. I mean, this is looking like kappa 1. Lambda 2 is looking like 1 plus, so I've got 2, n equals 0 to 2. Kappa from 1 plus kappa of 2 over 2 factorial. Now kappa of 1 was the first cumulant, which was the same as the first moment, which is the mean. And so this is equal to 1 plus the mean. And by the way, what is the mean in our situation? Well, the y to the s, remember we're looking at this should be the second moment minus mu squared, or whatever it was. It's kappa 2. We agreed the kappa 2 is always positive. Pardon me?
Kappa 2 was variant.
This was the variant. That's right. Kappa 2 was the variant, so this is already positive. The mean is actually 1 because the density function is just h of, right? It's just the mean is actually 1. So this is all positive. So interpreting lambda 2 in this fashion shows that it's positive. Now, in my colloquium talk, I showed you that kappa 3 and kappa 4 can be negative, but they're very, very small. It can be negative, so it doesn't, unfortunately, this is not going to, if the kappas were all positive, you're done. But they're not positive. Some other thorn in the whole process. So this leads one to study or come up with variations of this calculation. Yes?
Sir, the way you define kappa, therefore kappa 0 was not defined there. I mean, from kappa 1 we started counting.
Yeah, I think so. So what we would interpret is maybe 0 or
So
something.
left. Okay.
Yeah. Yeah, so one has to, all I'm doing is I'm just using the power series expansion here. That's all the difference. So in that case, is there a term here or not? Maybe there's a 0. Whatever it is, it might, whatever it is, it's not negative. Comes out to be.
No, non-negative is allowed.
Yeah, yeah. I agree, I have to be careful with the initial thing. So, this is where I think perhaps I have some time to talk about the Bomberi-Ligarius work. So, let me just comment that unfortunately, or fortunately, who knows? Unfortunately, kappa 3, kappa 4 can be negative, are negative actually. And therefore, the argument to say that these lambdas are positive because these guys are positive is not going to work. So, but they're not very, they're pretty close to 0 more or less. So after the paper by Jianjun Li, Ligarius and Bomberi kind of showed that the Riemann hypothesis is true if and only if for any epsilon positive, there exists a constant C of epsilon such that lambda n is bigger than C of epsilon, e to the epsilon n. E to the epsilon. Oh, with a minus sign, sorry, with a minus sign, that's the whole point, with a minus sign. So
you should put C of epsilon as positive.
C of F is positive, yes. There's some constant which depends on epsilon, so it's so you're allowing exponential growth, negative exponential growth, and so you're giving that freedom. Allows you, maybe there's hope, even if these silly things are negative, if they're not negative too badly, maybe there's some hope. That's where we are right now. And so, since some of you are interested in transcendental number theory, there is a transcendental number theory component to this whole study of this Lie constants, these lambda n's.
So the C epsilon, so you need this for all n?
Oh, this is for all n, yes. We need this for all n. So fix an epsilon.
I see.
If I have some epsilon, so if, there will always be some constants that's so if for some epsilon this happens, maybe that's a better way of saying it.
No, it's okay.
Yeah.
I mean, yeah, the
I can-
constant still can blow up.
Yes, you can. Okay, but that's the idea. So if there's if you have exponential growth, as long as, because if you have larger epsilon, it doesn't really matter. So some epsilon. Okay, so this is where we are. Now, coming back to this formula star, we can look at by the way, this observation I should point out, by first Vian and others. I think there's some person by the name of Yor or some. it's in the Bulletin of the American Math Society. And I think the article is talking about Brownian motion and probability and the zeta function. And the observation that the second the Lee constant, the second lambda 2, can be interpreted as a probabilistically as a moment or variance is due to Bian and other people. And there was a follow-up paper by Francis Brown, I suppose inspired by Osterley, where Francis Brown tries to develop this entire theory for Dirichlet functions. And then he comes across an obstacle. He realizes that there is no probabilistic interpretation of a Dirichlet function as of yet. So that h of y, mystery function h of y that Polya found, we don't have such things for general Dirichlet functions. That's a problem to be working on. At least if for small characters, maybe characters mod 4, characters mod 6, you can figure out what is it. It might be of some value. So we don't have the probabilistic interpretation of Dirichlet functions, so it's an open question. And what Francis Brown realizes is that because that's missing, he can't show lambda 2 is non-negative in the general case. Because if he could, he realizes that you've solved the Siegel zero problem. So the Siegel zero problem, which is notoriously famous unsolved problem, and apparently Zhang has made some breakthroughs, so we don't know the full story yet, but is connected with this business of lambda 2 for Dirichlet functions. Okay, having said all that, now let me try to say a few words about some sort of connection to transcendental number theory. So we have this formula here, like so. And we know that 2c of s is equal to s minus 1, pi to the minus s over 2, gamma s over 2, zeta s. We know this. This is the definition of c. So it's sitting here. Well, c of s. So I could, what is commonly done is you break this up into pieces. Like so. Break it up into pieces. And then lambda n can be, these pieces can be studied now. It will decompose. So one can decompose. I'm not going to do it here. One can decompose. Lambda n as an S0 of n plus S1 of n plus an S2 of n, where S0 is the contribution from pi to the minus s over 2 and this s to the n minus 1. One can easily figure that out. The second part, S1 of n, is coming from the piece, this piece. And remember, when you differentiate this thing, we get the digamma function. See, when you differentiate, we have a derivative operator. So you get these digamma functions. So, and that can be, it's well studied, and it can be controlled, and one can write down the contribution from that piece. Then the final piece is this last piece, s minus 1 zeta s. And that seems to be the mystery piece, because one can decompose this and show that S0 of n is, well, you can actually explicitly write it down. Whatever it is, I can just put O of n down. S1 of n, you can actually write down a n log m plus O of n. This is the work of Mark Coffey. And S2 of n is the mystery. So from the Bombiri-Lagarius perspective, everything is there because the other parts are O of n log n.
So in this lambda n, your definition of this lambda n from there, you are putting this, dividing it into three pieces.
Yeah, yeah. So s to the n minus 1 times this pi to the minus s over 2 is one piece and gives rise to s0. The other one is s gamma of s over 2, and then the other pieces from this, and you can check what the contributions are. So this will, the logarithm will then be log of a, log b, log c, and then you calculate this whole mess through that thing, and then you get these pieces. And all the pieces, the first pieces are all under control, but it's this last piece which perhaps requires some attention. So log of s, let's see how this works. I suppose log of, yeah, let's put log of s minus 1 zeta s is going to be log of, well, see zeta s is equal to 1 over s minus 1 plus this Euler constant plus these higher, what are called higher Euler constants. So on and so forth. So-called higher Euler constants. These are the Laurent coefficients of zeta s. Therefore, you can see s minus 1 zeta s is going to be a power series with these generalized Euler constants. Power series with generalized Euler constants. So just as you study gamma, you may study gamma 1, gamma 2, and all these higher constants. And there are many questions that you investigated for gamma perhaps and other things, generalizations of gamma and arithmetic progressions, gamma AQs and things like that, which lead you to linear forms and logarithms. You can study similar things for these higher things, and unfortunately they're not so simple linear forms and logarithms. They seem to be quadratic forms in logarithms, and then lambda cubic forms in logarithms, and so on and so forth. So these are higher kind of versions of that. So if I put s minus 1 zeta s, it's going to start off with 1 plus gamma s minus 1 plus gamma 1 s minus 1 squared dot dot dot. And you can see that whatever mess we have here in S2 is going to involve these coefficients. And how big do they get? Do they oscillate? You can actually show that they oscillate using Landau's theorem that I had indicated, that all of these things oscillate. If they didn't oscillate, I'm done. So they oscillate. So I think my advisor told me one time, if you prove a result which is perhaps what did he say? He said if you prove a result which is if you have a result which is probably of no value, you can probably prove it. Something like that. Because it's not going to be, it's probably right. Anyway, I don't want to put such pessimism on this project, but certainly these higher coefficients have certain mystery to them, and we don't know very much. So it seems to me that the Riemann hypothesis opens up a whole cosmos of ideas that relate back to arithmetic. I mean, these Euler constants are connected to arithmetic. Remember, I mentioned this famous equivalence of the Riemann hypothesis that was due to Guy Robin, that summation d divides n, d less than or equal to e to the gamma n log n for all n bigger than 5040. This is due to Guy Robin. Not Robin, Guy Robin, okay? That's how you pronounce the French name, Robin. So this is Euler's constant, and this is n log. Now, what is interesting here is that it's quite easy to prove that this divided by n log n in the limit is less than e to the gamma. It's quite easy, you know? So let me just kind of conclude my course of lectures on this humorous note. That I think you did it already or something. It's always very seductive, isn't it, to when you see such simple statements, you get enticed and you say maybe it can be done. So let me show you this small calculation, which is very cute, and you can convince yourself that surprisingly this last problem is hard. So the product, sum of the divisors of n, d, is, so if I were to divide, so this is a multiplicative function. So this would be 1 plus p plus p squared plus dot dot dot. And so if I were to, so p divides n, so this is, but if I did this, then I could certainly put this inequality down, because right? I mean, so this is equal to product p divides n. Maybe there's is there a simpler way, Tunga, to do this? How would you? Well, okay. I thought that because you were smiling, I thought maybe there was a simpler way. So, but you could. Let me just do it this way then. Let me point out first. Assume n is square free, so that I don't get into these powers. Assume n square free for the moment, so that this just becomes 1 plus p. Let's just assume n is square free for the time, right? So that I don't get into the quandary. P dividing n. Okay, let's get that. And when I divide out by n, summation d divides n, d divided by n, and that's going to be product p divides n, 1 plus 1 over p. Now, the number of primes that any natural number can have is at most log n by log 2. So, and this is maximized by taking the first log n over log 2 times. And this is certainly less than or equal to product p less than or equal to log n over log 2, 1 plus 1 over p. And this then is looking like this is equal to so sorry, this is less than or equal to 1 minus 1 over p, 1 minus 1 over p inverse, p less than or equal to log n over log 2. I mean, so I've put too many. So when you expand this, it'll be 1 plus 1 over p plus 1 over p squared. So I've just made it bigger. But now, you may know Murty's theorem. this is the Murty's theorem, that it's this product is asymptotic to e minus gamma log x. So therefore, this is asymptotic to e to the gamma of log n or log p. So it's asymptotically less than or equal to e to the gamma log n. So you certainly get the sum, sigma, sum of the divisors less than, asymptotically you'll get that, and then there's a little bit of cleaning to do for when the number is not square free. Small variation, which you can figure out. But it's actually easy to prove this asymptotically, but unfortunately, the asymptotic is not enough. Because the asymptotic says, what does it say? For n sufficiently large, it's the limit value plus an epsilon.
Yeah.
that turned epsilon is the problem. So there really is something subtle going on. No matter what way you try to approach the Riemann hypothesis, it will tantalize you as if you're very close, but then there's always some obstacle. So there's some interesting things. I can talk more about various equivalences of the Riemann hypothesis and whatnot, but I think maybe this is not a bad place to stop. Okay, thank you. Any questions?
Has anyone done the computations of lambda n to some extent?
Yes, they have. They have. As of course, you're going to get them to be positive because the Riemann hypothesis implies that. But they have done that, yeah. And now the interesting thing is that in Francis Brown's paper, you will find a quantitative version of Lee's criterion. So supposing you tested lambda n's are positive for n up to 1 million, let's say, then I believe his theorem is then n up to 10,000, all the zeros are on the line.
Okay.
So there's a correspondence. So if you checked it up to capital N, there's some function of n that he figures out. All the first f of n zeros are on the line. So there's that quantitative version. So everything has a quantitative version, which I think he worked up there. It's worth reading also, this paper.
Yeah, sir, you said the lambda 3, lambda 4, these are negative. So how can one negate that these are negative? I mean,
Pardon me?
what are the proofs?
Pardon me?
Lambda 3, lambda 4, these are negative.
No, not lambda 3, lambda 4. Kappa 3, kappa 3.
Oh, sorry, kappa 3, kappa 4, these are negative.
Yeah.
So how can we negate that?
Well, no, they are negative, but remember, it was the sum of the kappas. The other ones compensate, and it turns out to be positive, the whole sum. But remember, the formula was the lambda n was a summation of certain kappas, but the earlier kappas were positive, the later kappas may be negative, but they all combine to be positive. So the strategy to show that the kappas were always positive is not going to work. That's all I'm saying.
It's a reduction.
Yeah. Yeah.
Do we know explicitly the relation between these higher Euler constants and lambda?
Apart from these formulas that they produced, that's all. We only know that lambda n equals these Euler constants.
Log of whatever.
No, not log of. You could actually write down an expression of what lambda n is explicitly in terms of these Euler constants. Doesn't help, but you can. And I'm saying it's interesting from the perspective of transcendental number theory. If you're interested in that kind of stuff, it might be just in fact, this last piece has often been termed as the arithmetic part of the Lie formula. Somehow all the arithmetic is stuck in these higher constants. Okay. Any other